Thanks.
Xiaomin, for the very nice introduction and for inviting me. I'll talk about complexity without that I obtained, as Xiaomin said, MIP star equals to RE. It's a joint work with Anand Natarajan, Thomas Vidic, John Wright, and Henry Yuan. It's appeared earlier this year in our archive. And because of the connections of this problem to mathematics and physics and computer science, so I would first give you introduction of backgrounds, historical backgrounds of this problem and how it relates to different areas and the connections. So in computer science, we know that in the 30s, we know Turing defined what is computation by proposing a construction called Turing machines. And he also proposed a problem that determined whether a Turing machine terminates or not, the so-called halting problem, is undecidable. And later on in the 70s, complexity theory was developed. And in one important branch of complexity theory, we study the concept proofs, but through the lens of computation. A lot of important complexity classes such as MP, MA, IP, and so on are motivated by this kind of idea of verifying proofs computationally. And our work is actually related to multi-prover interactive proofs. And along the line, important result in complexity theory, and I think it's often referred to as the crowning jewel of complexity theory, is PCP theorem in the 90s. And it's a very special form of verification that we'll discuss more. And we use this as a tool for our proof. So because proof verification is important motivation and a lot of tools that we use from proof verification literature, I'll spend one more slide to talk about efficient proof verification. So this is a model where you have prover and verifier, and in the MP, the prover is trying to send the verifier a written proof, and then the deterministic machine V would need to determine whether to accept or reject in polynomial number of steps. So that's MP, and we don't know what is MP, but how it relates to, for example, P or other complexity classes. And as a generalization of this class, and also motivated by cryptographic motivations, people studied interactive versions of the proof verification procedure. So now you have a prover and also a verifier, and the prover can talk with the verifier in many rounds and polynomial number of rounds. And initially, people think that this is a slight modification of MP, and that the power should be very close to MP. But very soon, people notice that this is actually a very powerful class. And actually, we can show that IP equals P space. And normally, in complexity theory, we know that P space is conjectured to be much powerful than MP. And further generalizing this model, we can consider a situation where you have Alice and Bob. These are two provers who do not communicate, but they want to convince the verifier of certain facts. And that's the class MIP. And around the same time, people realize that this is another interesting class that's even more powerful than single prover case. And they prove that MIP equals NX. And it's interesting to mention that given the modifications of adding one more prover and also consider a randomness, we actually arrived at provable larger class of problems because we know that NX space is different from MP. So that's a brief introduction on literature of interaction proof systems. One result that I mentioned earlier that grew out of this kind of research is probabilistically checkable proofs. And in that model, you have, again, a verifier, but now you have a proof which is written in a string. There are two parameters. One is R, the number of random coins that the verifier would flip, and Q is the number of bits that the verifier would read from the proof. And for such a simple model, we have the PSP theorem says that if you have R, the number of coin flips to be of order log n, and Q to be some constant, then this class is exactly characterizing NP. So this is surprising because in NP we have, for example, a length and proof, and even to address this number of bits individually, we need to address send messages of order log n, and this is just the simplest case that you can imagine to verify NP statement. And also, there are a lot of different applications in algorithm and approximate algorithms and delegation of quantum computation of this fundamental result. There are also a lot of research on considering the quantum analogs of PCPs. For example, it is still a big open problem of whether there's a quantum PCP theorem for the Hamiltonian complexity theory. And so in our case, we would use this classical test, but we'll need some sort of quantum soundness later on. So that's a brief discussion of what we will use from computer science. And for physics, the problem is also started from the 30s, where Einstein and his co-authors are considering the behavior of entangled, joint quantum systems, and the concept of entanglement was proposed at the time. It's a very simple phenomena that you can see from two particle quantum systems. You can write a quantum state in this 0 and 1 basis, but you can also write it in different bases, like plus minus basis or this y basis. And these are called EPR states after the Einstein, Podolsky, and Rosen. And these are a source of fresh randomness. You can measure these two particles in different ways. Actually, you can measure it in Z, then you would observe random 0 or random 1. And if Alice measures 0, Bob would automatically always measure 0 if Bob also chooses to measure on the basis. So this is a very interesting phenomenon, and you can think of this as you have multiple ways of open the box. You have a box on two very far apart parties, and they have X and Y, like different measurements or different ways to open the box. And if you open the box in X basis, and you would always get plus and minus mass, it's a perfect correlation. But instead, if you measure Y, you would see different results all the time. So these are the puzzle that that's make Einstein and his courses wonder whether quantum mechanics is really a complete theory. But these kind of discussions, it's not purely philosophical discussions. Nowadays we know that this concept of entanglement are the resources that enables a lot of interesting applications, including the satellite that the Mauritius satellite that China has. But at that time it is a big puzzle to them, and they, like Einstein and Bohr in 75, they asked the question of, can quantum mechanical descriptions of physical reality be considered complete, and published 2 papers with the same title in Physical Review, and debate their understandings of physics and quantum mechanics. So the solution to this debate come much later on in the 60s, when John Bell come up with what we now know as Bell inequality. It's a very simple experiment that you can do to tell apart whether Einstein's interpretation or the quantum mechanical interpretation is true. That whether you can test whether the world is classical or quantum. Nowadays, there are experiments that you can do in labs that are proven to be loophole free, and be confident that the world is actually quantum. And that's a picture where an experiment had been done in Delft a few years ago. So that's in physics. And the mathematics part of the connection is, again, in the 30s, John von Neumann studied what we now call von Neumann algebras. I guess this is not a coincidence because he is trying to lay the foundation of quantum mechanics at the time, so studied operator structures of that physicists use in quantum field theory and so on, quantum mechanics. But now, because it's a mathematical foundation and it's a purely mathematical research area, and a lot of mathematicians have contributed to that area. And for mathematicians, it's an important problem to consider the classification problem. What are these algebras like out there up to isomorphisms? And in a paper by a French mathematician, Alain Kahn, in the 70s, he studied the classification of von Neumann algebras. And in that paper, there's a line asking the question of whether or type 2 one-factors can be embedded in some hyperfinite factors. So it's not that easy to digest what it means, but it's a very important problem. It's not that immediate, like after maybe 10, 15 years, nobody actually paid much attention. But the importance becomes clear when a lot of different mathematical problems are shown to be equivalent to this embedding problem. So one problem is Kirchberg's QWEP conjecture. It relates to the structure of tensor products of C-star algebras. And also more close to this work is a question asked by Tsirison, when he's trying to study the theory, that mathematical theory behind Bell inequalities and non-locality. And so he asked a question of can finite quantum systems approximate infinite systems? And there's a lot of previous research showing that these two problems are all equivalent to Columns embedding problem. So we will later on, we won't be able to tell you what are these mathematical problems, but we will define what is Tsirison problem later on in the talk. So this is like a high-level overview of what we did. We use computer science tools and also some quantum information theory tools to address problems in both mathematics and physics with a very long history. To give you a closer look of what we are studying here, we consider now entangled provers. Like we've been talking to MIP, where provers are not communicating and want to convince a verifier of certain fact. In this generalization or quantum analog of this model, Alice and Bob can share a quantum state to begin with. And essentially, we are considering the difference of shared entanglement and shared randomness in these two different setups. And it's interesting perspective to see that actually this is something called quantum interactive proof is essentially what we physicists study in foundations of quantum mechanics, and it's so-called Bell inequalities. So basically, in terms of the interactive proof systems, this is can be think of as a soundness problem, because when you have entanglement, the value is higher, and previously sound systems would no longer be sound, and it could be a problem. And we will see a lot of discussions around that. But more importantly, this connection between Bell inequalities and multi-prover interactive proofs opens the door to use of many powerful ideas in interactive proofs developed by computer scientists, including low-degree tests, pair repetitions, and PCPs. And fortunately, we can combine all these interesting ideas together to make the proof work. It is inconvenient to use the language of non-local games. In a non-local game, you have, again, two provers, and you have finite question sets, X and Y, and finite answer sets, A and B. We have a question distribution mu over X and Y, and then a decider. So given an input question and answer pair, whether the verifier would accept or reject. To give you a very simple example, the Momi-Imperius Magic Square game is one of my favorite game. It's very elegant. So this is how we can visualize this game. It has 8 variables arranged in 3 rows and 3 columns. And this is a constraint system that each row has even parity and each column has odd parity. So these are binary variables, and so x1 plus x2 plus x3 is 0, and x1 plus x4 plus x7 is 1. You know that this is a constraint system with no classical solution, because when you sum over all the variables by rows, you get 0, and if you sum over all the variables by columns, you get 1. But you can, nevertheless, you can turn this into a two-prover game where Alice is given maybe a column, and Bob is given one variable of the column, and we would accept if the constraints are satisfied, and Alice and Bob give consistent answers on this shared variable, in our case x6. So this is a way that we can transform a set of constraints into two-prover game, and that's a standard constraint variable game for CSPs, and in our case it's 6 constraints over 9 variables. In our discussion, we'd also consider families of non-local games, because to argue that decidability, it's convenient to consider a family of games rather than a single game. So we define a family of games using Turing machines, in some sense, as uniform families of games. So a verifier V is a pair of Turing machines S and D. S is a Turing machine that taking care of the sampling procedure. So basically, Z, like you can sample, you can generate random seed Z, and then apply some function L A and L B, and that would be the question for Alice, and that would be the question for Bob. And S is modeling the behavior of L A and L B. And Turing machine D is the decider, modeling the decider using the Turing machine. And we would say that the nth game of the verifier, denoted by Vn, is defined by Sn and Dn. So we just fix the first input to some integer n. Given a game, we can define 2 different values. One is called entangled value, and it's a tuple of a state and measurement. So the state is shared between 2 Hilbert spaces, HA tends to HB, and A, B are measurement indexed by question X and Y. The entangled value is then the optimal winning probability of the strategies that entangled strategies that you can choose, that the provers can use. So, but it's a super or strategies, and then it's expectation. That's the expression that in quantum mechanics we know that that's how the verifier would accept. So basically, this is a number between 0 and 1, and it's winning probability of the provers. And MIP star is then a class that corresponds to the approximation of the value. We would also need to consider a converging operator value, and it's very similar to the previous definition of entangled value, but now you only have a single Hilbert space H, and so because it's a single space, you don't have tensor structure, and the locality of Alice and Bob are modeled by A's operators, and B's operators are commuting with each other. And similarly, you can define the maximum winning strategy, meaning probability as a commuting operator value. And the Tilson's problem that we asked before is asking whether these 2 values are the same for all games. It's interesting to mention that if you consider finite dimensional Hilbert spaces, then these two values are the same, meaning that all these finite dimensional computing structures has tensor equivalent strategies. So the problem is only interesting when H, the Hilbert space, is infinite dimensional. And regarding to these values, we have two algorithms. Algorithm one is very simple. You just do an exhaustive search for better tensor product strategies of increasing dimensions and precisions. So that would give you a sequence of values approaching this entangled value from below. The other algorithm is non-trivial. It's a non-commutative sum of square SDP hierarchy technique. In mathematics, it's called the positive Stelan sets. What this algorithm will give you is a sequence of values that approach the commuting operator value from above. And so these two algorithms actually give us interesting consequences on the complexity of MAP star. The first algorithm tells us that MAP star is in RE because if the value is high, then essentially there will be a total machine that uses this strategy to detect that. But more importantly, the Thurston problem would have, if Thurston problem has a positive answer, then we know that these two values are the same, and we have two algorithms, and basically you can come up with an algorithm to approximate the entangled value by alternating algorithm 1 and algorithm 2. And in complexity theory terms, MAP star will be in the set R, which is the intersection of RE and then co-RE. And there are like more than 15 years of active research on this class, MAP star, and we'll give you a bit of introduction of what happened in this 15 years. In the first 5 years, basically, like in 2004, Cleve et al., they defined the problem and make the connection to notice the soundness problem and connection to the Bell inequalities. What are the soundness problem again? Though it's most convenient to see this in the example of Mermin-Pierce magic square game. We have defined the game previously. It's motivated by the constraint system here, and classically this is an unsatisfying system. So the classical value of the game is almost 1, and that's what we call soundness, even though it's a weak soundness. Like this system is not satisfied; it has no satisfying assignment, so the value cannot be 1. But unfortunately, the quantum value of the game is 1. And there's a very simple strategy using 2 EPRs and party measurements. So in some sense, the system of constraints and defining a game, and this game is previously sound classically, but it's not sound quantumly, and then what we call a soundness problem. And people start to wonder whether this is kind of a bug, like you cause problems in interactive proof systems, like entanglement could be a bug, or maybe it's a feature. And sometimes it's indeed a big problem because we know that at least for 2-proof XOR games, where the freeze decision is depending only on the parity of the player's answers, the complexity of the 2-proof interactive proofs with entanglement is inside P space using a result of Werner. But classically, this class is as powerful as MIP in general, so it's an exp. And if you believe that these two classes is different, then actually using entanglement could be a problem. It breaks like a lot of protocols here that are quantumly classically sound is not quantum sound, and it's not fixable because of the complexity classes separations. And also, like in unique games with entangled provers, it's easy. and classically we don't know with the complexity of unique games. So in some sense, that's an unfixable bug that entanglement has caused to interactive proof systems. But if you are considering general form of interactive proofs, there are many techniques that you can enforce the behavior of the players, so that entanglement won't be that useful. And that's a picture that shows that you can design some constructions on prover side so that entanglement isn't really an issue. And so using this kind of techniques, so-called entanglement-resistant techniques, we can show a lot of results, such as non-local games or MP hard. So previously we are not even able to do that. And the breakthrough result by Ito Vedic is showing that for all problems that in NEXP, we can construct MLP style protocol. Basically, the quantum class is at least not smaller than the classical class. And in some sense, the bug is fixed because everything that you have a classical interactive system, you can have a quantum interactive system. The next 5 years in the history is more about how do we use entanglement in the positive. So because like the provers share entanglement and the hardness of the system is previously what we can show is MP or NX, but they are very classical classes, and there has been a period of time that people are trying to generalize or enhance this kind of complexity to quantum hardness, like quantum analogs of MP. And that's first done by Fitzsimons and Vidic, showing that you can design games for QMA, and that's an idea of combining quantum error detecting codes and with rigidity type of argument. So rigidity, so this error detecting code technique wasn't used in our final proof, but rigidity is an essential ingredient. So I'll spend a bit more to describe what it is to have rigidity for a game. So for example, the Magic Square game has rigidity, and basically when you have like the provers Alice and Bob have a strategy that's close to 1 minus epsilon, that's almost perfect, then the measurement assigned to the variable x1, x5 has to anti-commute. It is exactly anti-commuting in the strategy for the value 1 strategy of the Magic Square game. But even if you know that you have almost close to optimal strategy, you have a structural result of anti-commutativity between these observables. And from the anti-commutativity, you would know that these are actually X and Z measurement. So in some sense, this is a result of approximate representation of this group of sigma X and sigma Z generated by these two generators. And the statement says that if you have approximate representation of this group, you can round it to exact representations. And this result can be generalized to all finite groups by Gauss and Hatomi. Trying to improving on this QME hardness, we propose proof systems, improve the hardness of the lower bound to from NX to NNIC and triple exponential non-deterministic time, but the problem is like for all this kind of improvement, the gap is shrinking. The gap is getting smaller and smaller with the parameter with the size n, but we notice that if we can do gap amplification, then we would be very close to prove undesirability of MIP star. And indeed, there are several improvements on that, and in this paper and Vidic, they combined low degree test and generalized it to a quantum version. Basically, it's given us a polybasis game, which is a very powerful self-test for the poly group, and it's efficient to addressing this in EPRs. The communication is only polylogarithmic, and this building upon this kind of techniques and also compression techniques, and the trilogy on the right was able to show that double exponential non-atomic time is in MIP star. And this is the first time that it's shown that MIP star is different from MIP. Now on, we know that entanglement actually are features. Very important in our final proof, and basically it's a rope around the quantum low rigidity. This is how it states. Any game where W, then to measure poly X or Z and respond with answer bits. And in some sense, that's rounding the approximate representations for the poly group. And it's more, it uses a lot of instances of magic square in that polybasis game. But overall, you can think of this as approximate representation result for the poly group. So our main result is then we have shown that M star equals to I, and therefore no algorithms can approximate this value because the problem is as hard as halting, and this gives complete characterization of MIP star, and the answer is really a surprise to all of us. So what we call spooky complexity, it's the biggest possible, like it's in RE, it's as hard as the halting problem. And because of the connection that I mentioned earlier, that decidability of this class is actually related to Thurston's problem, and we gave a negative answer to Thurston's problem and also Kahn's embedding problem. So the proof overview, the essential part that technique is compression defined by a family of like a pair of Turing machines. We compress it to and get another defining the communications are smaller in some sense. And so that's the completeness says that if the big game has value 1, then the compressed game has value 1. Otherwise, if the big game has value at most half, then the compressed game has value at most half. And there's a condition on the number of EPR pairs, or amount of entanglement that we need to use in the compressed game. So once we have this compression theorem, it's very easy to prove that you can convert the problem, or reduce the problem of whether a Turing machine M is halting or not to two-prover protocol, and the problem of whether M is halting is reduced to whether the value of this game is 1 or at most a half. And for this, we need to use the Kleene recursion theorem. So basically, because in the definition of this Turing machine D hat, the decider of this verifier that we define, it was similarly M for second step, if this hasn't the Turing machine itself, and then you compute the the compressed Turing machine S sharp and D sharp, and accept only if the compressed decider accepts. And we know that, noting that the definition of this Turing machine uses the description of it itself, and that's something you can do for Turing machines, and that's what Kleene recursion theorem guarantees. So now what remains to talk about is how do we actually show that compression theorem, that you can at least for a family of games, you can start with a big game and end up with a very small game. And it consists of four steps. And the first step is called introspection. In that step, the verifier would have smaller question sizes. And then it's autocorrelation step. It's an easy step, a pre-processing step for using PCP constructions in the next step. So in PCP, what we can achieve is we can reduce the answer size. And finally, because along the way we have lose some of the gap, we need to do some pre-repetition to recover the gap. But what we should make sure is that the question and answer are getting smaller in each of these iterations. So as you can see, like introspection and PCP are the interesting steps. And intuitively, what these two steps are doing is like the verifier saying, "I'm lazy. How about you two provers come up with the question yourselves? Answer these questions and prove to me that I would have accepted the questions and answers in the first place." And that's a very, very interesting idea. And to do this, we need to exploit the power in like the features of entanglement. And actually, EPRs are able to allow us to do question sampling, and that's the introspection step. You can enforce the players to sample a very big distribution and with interesting correlations, and use that as a big question for the big game. What we need to do, technically, what we need to show is we want to be able to show that you can do it recursively and without losing the gap, to gap preserving compression of so-called normal form. It's not for all stupora protocols. It's for a family of rich enough protocols, what we call normal form, and it's a two-prover one-round protocol using EPRs. So to conclude, the technical idea is to show that you can actually do a recursive gap preserving compression. Unfortunately, I don't have much time to go into the details, but that's how we prove this compression theorem. And once you have the compression theorem, you can use Kleene's recursion theorem to prove that RE is actually contained in MIP star. You can reduce the halting problem to the decision of whether the value of a game is big or small. And then this equality follows from the containment of MIP star in RE using algorithm 1 that we talked about earlier in the talk. And this gives negative answers to Tillerson's problem and Collins embedding problem. So the open problems, one is, can we find simpler proofs? Our proof is complicated and long, even though it's modularized. And an interesting question is what's the power of the commuting operator model? We believe that it's co-RE, but for that we need to develop another version of quantum low degree test, and for the explicit construction of counterexamples to Collins embedding problem conjecture, our result is indirect proof that this conjecture or this problem has an active answer, and we don't have example of a concrete example where you cannot embed in that mathematical language. So thank you for your attention. That's all I want to tell you about this result. And last slide is advancement of our opportunities for students. If you're watching this online, and that's where you can find opportunities that like for universities in Sydney are hiring PhD students.
Thanks, Zhangfeng, for the excellent talk. Okay, I have some questions first. So you show that MIP star equals RE. So what happens if we consider the QMIP?
QMIP, I guess you mean that you have a quantum verifier and send quantum messages, right?
Yeah.
Provers are still allowed to use entanglement. And in that model, we know that it doesn't really help. It's the same class. So you can for any such a particle, you can come up with a particle where the verifier is classical, message is classical.
Okay.
That's before our result.
Okay. Another question is because your open problem tool. I'm wondering what happened. Are there any model that for the interactive proof system? Can we put some oracle to it to enhance the power?
I guess people have studied such versions where you have oracles, but I don't know, like you already without oracles you have power of RE. What kind of oracle you are trying to implant?
But above RE there's also a hierarchy.
Yeah, so actually like the zero error cases are interesting. Like I think Henry has a paper with his students showing that the power can be beyond RE and co-RE if you consider zero error variants of this classes, but it's not using oracles. I don't know, like you can consider a version where you have, but it's not like, because it's not, I think like before our results, nobody would believe that it's
that's true.
And it's not. I don't see any result that talk about implanting a super powerful like oracle in that model, because it doesn't. You don't have that motivation of doing that.
Okay. So at some step, you mentioned the RE intersection with co-RE. So are there any formal characterization of that class?
What you mean?
Oh, so it's just a recursive. Okay, I see. Sorry for that. Okay. Another question is that basically you solve the terrorism problem. These two are whether they are equal is undecidable. But for a particular terrorism type inequality, is the value computable?
Oh, sure. Like for special classes of or special instances, definitely we know that at least like for CHSH, we know.
Yeah.
Our result just says that there's no like universal like algorithm for doing that. There's no algorithm that solves all the problems.
Okay. But if we restrict, as you said, restrict the power of entanglement, is it computable or approximatable?
Well, sure. Like the amount of entanglement is key to this question. Otherwise, you cannot have that amount of power, because I guess the first paper on quantum interactive proof systems is I don't remember the name of authors, but what they show is if the number of entangled pair, like GPR pairs are polynomial, then the class is the same as the quantum class is the same as the classical class. You don't gain extra power if the number of EPRs is polynomial. You have to like super polynomial number of EPRs, and the players are doing very complicated measurements in order to have such like powerful.
Okay. Does that mean the value? I mean, if there's only polynomial EPR pairs, the value is computable in P space, or what would be the upper bound?
Yeah, like I think it depends on the amount of entanglement. Once you have a bound on the dimension, like algorithm one would be the algorithm that you can use.
The brute force.
But like I think there's a recent result that beats brute force. So you can do better than brute force. Like I don't know what the exact form of complexity. Like once you have a dimension d, what's the complexity? Maybe it's some non-deterministic time or deterministic time, like depending on the size of dimension.
Okay. I think I already answered too many questions. So, are there any questions from the room? I mean the Zoom room, or any other questions from the Bilibili? If you have a question, you can directly unmute if someone have a question. Okay, I think here's a question, but I'm not sure. I really understand it. Okay, basically, I think maybe the question is about the consequence, or whether the technique can be used for other problem. That's my translation.
Okay, I think the technique, if you look at the proof, basically we use this quantum low degree test and quantum polybasis game. This is a very powerful tool. And another idea is introspection, that you can ask the provers to generate a large number of randomness, and that's verifiable, that you know what they are generating. And it's not like a simple distribution. You can generate complicated distributions. And I think this kind of techniques could be helpful in, for example, considering delegations of quantum computations. Like you can make the error super efficient without doing much work. The players are sampling questions themselves using EPRs, and the verifier would only check very small informations and computations. So and also mathematically, I think our technique could be helpful to understand the problems that are open. In presentations, approximate representations, like they have, you're considering a problem called hyperfinite groups, and also a Sophie group problem. Like, but it's hopeful that if we can distill mathematical ingredients from a proof, it may be helpful to resolve problems in their literature. That's my guess.
Okay, I have a further question. So, because you use the classical PCP, so are there any the quantum PCP, and what's the state of that direction?
So quantum PCP has two versions. One is what we use called games version. So the games version is, the test is classical. It's exactly the same test that you would use in the classical sense. But what we need is that this test is sound against quantum provers, so that provers who use entanglement cannot have a significant advantage. Basically, for example, in low-degree test, you are asking the provers to encode information using low-degree polynomials, and they have to do so because otherwise you would reject classically. And what we require is that even provers have entanglement.
Yes.
When you pass the test, you are essentially doing the same. You have some sort of polynomial in your head, like in your mind, or you would do a measurement to get the polynomial, and then you respond the question using that polynomial. That's allowed, but otherwise, so we can get sort of this structural results even in the quantum case. That's what we call quantum soundness. The other version is related to the Hamiltonian complexity version. It's like you have n-qubit system and you have Hamiltonians, like it's a quantum analog of CSP problems, and you can consider PCP problem over there, whether like the gap, you can amplify the gap as in the CSPs, like the ratio of satisfying whether the errors can be detected with constant probability. That we don't know. That's a still open problem in quantum complexity theory. And previously for because I guess it's now very clear that the games version are more flexible because operator structures are much like you don't have to respect any qubit structure, and there's no n-qubit there. It's just a very big measurement operator. It doesn't say what space it's marrying on. So the connection is basically broken. And yeah, but we don't. But maybe for the problem of delegation of quantum computation, there's still a possibility that under restrictions of how these operators can live on, or what, like in that, like as you asked, what happens when you have a dimension bound, and maybe in that case you can still recover certain connections between this. It's very so much about it. Yeah, I guess the connection isn't good, right? Can you?
Yeah, not very stable. Is now okay?
Yeah, I can hear you.
Okay. So do you believe the Hamiltonian version is true or not?
I don't know. Because there are positive and negative evidences.
Okay.
Yeah.
Okay.
Maybe I don't know. It's too soon to tell.
Okay. Thank you very much. Thanks for the nice talk. If there are no further question, let's thank Chief Zhengfeng again. Okay. So this is the end of this session. Thanks Zhengfeng, and also thanks Tongyang. And the next session will start at 1 p.m. Okay, there's another 3 talks.